Oh, hey, I didn't see you over there. Sorry, I'm just finishing some of my couch potato brand snacks. One moment. Ah, wow, those are good. You should try to get some. Okay. Well, as you can see, we're going to discuss today why do we use the t-distribution for sample means. You might recall in the past, we had this thing called the central limit theorem that said that sample means are distributed normally. The mean of those sample means is equal to the mean of the population. And the standard deviation of those sample means is equal to the standard deviation of the population over radical n. And that's all well and good. The only problem is, I want you to see these two populations down here, both of these yellow sort of background distributions. These are parent populations. Something incredible about them is that they look extremely different. However, they both have the same mean. So the issue being, when we draw from a population and we're studying the mean of that population, so the mean is unknown. Another thing that's unknown is the standard deviation, right? These two parent populations have the same exact mean, but very different standard deviations. And so due to the fact that these two quantities are unknown about the parents, means that there's this extra variability that is not built into the central limit theorem when we're studying X bars. The central limit theorem works perfectly if we knew the parent population's shape, standard deviation, all that stuff. However, it does not quite work in practice if we do not know the standard deviation of the parent population. Okay, so this is a big issue, and we're going to discuss somebody that noticed this issue and actually solved this problem. But first, you might be thinking, why wasn't this an issue when we were studying proportions? So recall that proportions, p hats were distributed normally with the mean. The mean of the p hat distribution was equal to the parent population proportion p, and the standard deviation of p hats, or the standard error, was equal to radical pq over n. And of course, as long as the conditions are met. Now, the thing is, p itself is, it's something that studies or helps us study qualitative data or categorical data. So if we're studying P, then really our population is broken up into, a proportion of successes and a proportion of failures. So when we're drawing from a population, and it turns out that, let's say that the parent population's proportion of success is 42%, then every single other population whose proportion of success is 42% will look just like that population one. So you can see here there are two populations, and both of them have a 42% success rate, and they both look identical, right? And this is the only way a population can look if it has a 42% success rate. However, going back here, when we're studying means, when we're studying a quantitative variable, there's other things that cause variability, okay? Not only what is the center of the parent population, but what's the shape? What is the standard error, or the standard deviation, I should say, of the parent population? So on and so forth. So this is why in practice it turned out that the normal model did not work when we were studying sample means. Okay. Enter this man, William S. Gossett. So I know what you're thinking. Why is he wearing like 15 very heavy shirts? All I can tell you is I heard it was colder back then, so maybe that's part of it. Or he just wanted to look nice and warm. But that's the man. And we actually owe him a debt of gratitude because he discovered what is called the T distribution. So just a brief little history of this guy. He was a quality control engineer for Guinness Brewery in Dublin, Ireland. So that's just a type of beer. And the idea was that he was hired to test the saccharin level in this beer. And he wanted to make sure that the batches had the appropriate level. They didn't want it to be too high. They didn't want it to be too low. Okay. And so that it was his job to just take a few samples, so a small number of samples from an entire batch, and decide, okay, yes, this is good, or no, this is not good. And he did this by using a hypothesis test. But the thing is, the sample sizes were very, very small for a number of reasons. Of course, he didn't want to be drinking a ton of beer on the job. And also, every drop of beer that he drank, then that was a drop of beer that Guinness Brewery couldn't sell. So there were many reasons for wanting to limit the number of the sample size. All right. So essentially, he used an alpha level of 0.05, but the problem was, and here's just like an example of hypothetical. I don't know this for sure, but here's what I'm thinking his hypothesis test looked like. And of course, this should be alternative. Okay. But using an alpha level of 0.05, he actually ended up rejecting good batches 15% of the time. Now let's think about this. If he's rejecting good batches, and look, here's his null hypothesis that the average saccharin level is equal to some appropriate level. The alternative is that the average saccharin level is not equal to some appropriate saccharin level. So if he's rejecting good batches, a good batch would mean that mu is equal to some appropriate saccharin level. So he's rejecting the null hypothesis 15% of the time, even when it happens to be true. So he's making an error. What type of an error is this? I'd like you to pause and think about that for a moment. Okay, welcome back. Hopefully you thought about it. He's making a type 1 error. And as we discussed, how often should you make a type 1 error? Well, remember, probability of a type 1 error is equal to alpha. And so, yes, this person would make errors, or it's built in, it's known that he is going to make an error some percentage of the time, and it should really only be 5%. But he's up there making errors 15% of the time. So something's going on, he noticed. Okay, and so this is just a diagram of what his rejection region might have looked like with the normal model. Okay, and this is his alpha level of 0.05. It's a two-tailed test, and this is the distribution of X bars. And of course, we're assuming, sorry, one second. We're assuming the normal model with, the appropriate parameters. But again, he noticed that this model was failing a lot more often than it should. It should only fail 5% of the time. It was failing 15% of the time. Okay, as this says. So what was going on? Well, he realized that due to the small samples, the sampling distributions that he was studying, they should not and could not be modeled using the normal model. And of course, one of the major reasons for this additional variability is what we discussed at the beginning of the video, the fact that not only is the mean unknown of the parent population, but so is the shape and standard deviation. All right, so this guy actually took time off and went to study the problem, and he actually developed something called the T distribution. And he noticed that when he applied this distribution to his practice, he was making the more appropriate, type 1 error about 5% of the time. Okay, So it is thanks to William S. Gossett that we use the t-distribution. Now, how does the t-distribution compare to the normal distribution? Well, one of the major differences, I mean, the shapes are pretty similar. They're symmetric, they're mound shaped, they're peaked at the middle. But the major difference that you can see in the t-distribution is that the tails are much, much larger, okay? And so let's say we have an alpha level of 0.05. Well, in the standard normal, in the normal model, if we had an alpha level of 0.05, and let's just assume upper tail test for now. If we have, in the normal model, if we have an alpha level of 0.05, our rejection region might be over here. But in the t-distribution, right, and of course this is 5% of the area of this of the overall normal model. But in the t-distribution, due to the larger tails, where do you think this rejection region gets located? Does it move to the left or does it move to the right? I'd like you to think about that for a moment. Okay, welcome back. Well, if alpha is still 0.05, then since there are larger tails, there's a lot more area in those tails, and our rejection region actually gets moved over to the right, so farther away from the center. So this area over here would be the rejection region for this same problem if we're using a t-distribution. So as you can see, what the t-distribution does is it allows for our samples to be a little bit more variable, and it makes it a little bit, makes it so that we have to get a much higher t-score in order to reject the sample, in order to reject the null hypothesis. So in essence, we need to get a really crazy sample for us to be able to reject the null hypothesis, okay? And here you see the t-distribution for different sample sizes. So as you can see, as the sample size increases, the shape of the distribution actually does slightly change. So the yellow distribution that you're looking at, that's with a small sample size. The tails are the largest. And when we see V, you see this over here, V equals positive infinity. That's when the sample size is the largest, and you notice the tail is the smallest. So as the sample size increases, we're actually a little bit more sure of our sample. And so therefore, the need for additional variability is reduced. And so the tails become smaller and smaller and smaller because we don't need to allow for that additional variability. And actually, as it turns out, as n approaches infinity, so as sample sizes get really large, the t-distribution will in fact approach the normal distribution. Okay, so for really large sample sizes, t and n are essentially the same exact curve. Okay, so that's a brief understanding for you about why we use the t-distribution when studying means. And in the next video, which should come out a little bit later today, we're going to put it into practice. So we're going to solve this problem: plan, justify, show, summarize. Let me fix this mistake. I know I made a lot of mistakes in the last video, but I'm trying my best here. But anyway, our goal is to estimate mu of X for the following population. So newborns in the United States, we want X represents a newborn baby's weight. Sigma X is unknown, of course. You know, in general, we don't know what if we don't know the mean of the population, it's very unlikely we're going to know the standard deviation of the population. So what we do is we estimate sigma X of the population by using whatever the sample's standard deviation is. And I'll go into more details a little bit, like I said, in the next video. And our sample of 9 babies had an average birth weight of 9.2 pounds. Okay, like I said, we'll get into that in the next video, but you should really at least attempt this on your own. What exactly is this question asking you to do? How might you approach it? So on and so forth. Anyway, ladies and gentlemen, until then, please be well. I hope you're enjoying yourselves, and look out for those couch potato brand snacks. All right. See ya next time.